Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Welcome to Schweitzer Drive. I'm Dave Whitehead, the CEO of Schweitzer Engineering Laboratories, and today we're going to delve into the physics and talk about a topic that tends to get really hyped up in some circles and can generate a lot of worry from other people. That topic is electromagnetic pulses, or EMP. And I'm going to be talking with SEL's director, Travis Mooney. Travis has been with SEL since 1995. Travis has developed probably a quarter of all the products we're shipping today. And as part of being able to develop all those products, he puts these devices through a torture test of all kinds of electric shocks and zaps and everything else, which is sort of akin to EMP, but we're going to get into that in a little bit. Over the years, Travis has played a key role in developing SEL's EMP mitigation strategies and really helping out our industry understand what the effects of HEMP, and I'll get into that in just a second, might be on electronic devices designed to be in substations that already have to withstand a whole host of electrical phenomena, whether it's switching events, lightning strikes, etc. But with that, let's get into this. Hi, Travis. Welcome to the show.
Good afternoon, Dave. Thanks for having me.
Well, it's our pleasure to have you, and we're looking forward to this discussion. So let's really, right out of the gate, let's start with what is EMP or HEMP, and what are the differences between the two?
So an electromagnetic pulse can occur anytime you have a rapid change of current over a marginal distance. So I think the one that we've experienced most is just electrostatic discharge in the wintertime. You shuffle across a carpet, you touch a piece of metal, you see a spark, and that creates an EMP. And if you're sensitive enough to hear it with your ears, if there's a speaker nearby, you might hear a crack. So that's the effect of this pulse propagating through air and then coupling onto the speaker wires. Now
hemp has got to be a little bit different though, right?
Yep.
More than a little crackling
hemp
on my
is
speakers?
a little bit different, a little bit crackling. So that occurs when you've got a nuclear weapon that's detonated 30 kilometers or higher above the Earth or into the Earth's atmosphere. And that explosion creates gamma rays, which interact with the Earth's atmosphere and strips electrons away from the Earth's atmosphere. Now, our magnetic field of the Earth rapidly aligns and deflects those electrons, which creates a pulse. And that pulse can propagate down and illuminate a wide area.
And so can you share a little bit of history of hemp or EMP and why this topic continues to worry folks today?
I talk a lot about the effects of HEMP on the grid. And a lot of people come up to me afterwards and they ask, Travis, what about my home electronics? What about our automobiles? Well, HEMP has the greatest effect on things that are connected to the grid. So things that would be plugged into an electrical outlet. Devices like iPhones have proven extremely resilient, as have automobiles. So there was a test lab that subjected automobiles to 300 kilovolts per meter, which is 6 times greater than the baseline event. And 1 out of 10 of those cars shut down and had to be restarted, but in no case was an automobile damaged. So the first effects were observed when the United States detonated a nuclear weapon above Johnston Island, and that created an effect in Oahu. And residents of Oahu saw some fuses blow, some radio interference occurred, and of course, when the fuses blew, some lights went out. But the interesting thing to note there was that power in general still remained in Oahu. Some fuses blew, some electronic devices were damaged, but not all.
So then I guess today that there's a natural extrapolation that is, man, this was back in the late 40s, early 50s when these tests were going on, and way over in Hawaii, there was lights that were getting turned off. With society now so dependent on electricity, so dependent on electronic devices that if something like this were to happen, gosh, we'd all be back in the Stone Age.
So that is the concern, just the wide area effect that this can have. Now, we've got a lot of experience with electromagnetic events in general. The biggest electromagnetic event that happens frequently in the United States is lightning, right? And that's a pretty high energy event. In fact, there's more energy in a lightning strike close in than there would be by an HEMP. And I think you'll remember this, Dave, when we used to communicate over telephone modems in our computer, and those would get damaged.
I'm old enough to remember that. Yeah,
exactly. And I lost a few hard drives. I lost some modems. I lost some computers. But now we've got surge suppression devices, right? We've got industry standards that have advanced to protect the electronic equipment against lightning strikes. And that gives us a good measure of resiliency against all EMPs, HEMP included.
Hey, let's talk about HEMP and really, you brought up maybe part of it is similar to lightning strikes. Maybe you could describe to us what an HEMP event consists of. And do it so that technical people really get a kick out of it, but my mom can also understand it.
Exactly. So we talked about some of the EMP events that occur in nature. So we've got lightning, we've got electrostatic discharge, we've got sparks that occur when any breaker opens and interrupts some manner of current. And then you've got the northern lights, which is another form of an electromagnetic event. So all of these events exist in nature. And when an HEMP occurs, you can analyze that waveform and break it down into constituent parts that resemble the EMPs that we just spoke about.
I know there's E1, E2, E3. Yeah. What are those various parts of the waveform analogous to?
So the E1 event, so if you Google HEMP, you'll see those terms used. So the E1 event or early time event looks a lot like electrostatic discharge or very fast AM, FM pulses or just breakers opening. That's
what's the time scale we're talking about?
An E1 event lasts nanoseconds, which is a billionth of a second. So to put that into perspective, we would have to live 32 years before we'd live a billion seconds. And then you have the E2 event, which is 1,000 times slower than that. And it lasts millions of seconds, which is still imperceptibly fast for a human.
And stepping back to the E1, so it's very, very short nanoseconds, but a lot of energy.
Yeah, a lot of
energy for a very, very short time. Yep. E2, less energy, but for a longer time. Not a lot of time, right? Yeah. We're still talking microseconds-ish stuff. Okay. And then there's a third part to it?
Yeah, the E3 or late time. And that looks a lot like the northern lights or a coronal mass ejection. And it fluctuates for seconds and can persist for hours. So much, much slower.
Okay, that's great. And just for reference, then you talked about, you guys design the stuff that hangs on poles to get blasted by lightning all the time, right? So we're very familiar with protecting against this E2 of the E1, E2, E3 type of time and energy that gets put into these things.
Yeah, and we also have tests that do a pretty good job with the E1 part of it,
True
right?
enough.
So electrostatic discharge is really close. Electrical fast transient burst testing that we do that simulates the arcs and sparks that occur when a breaker opens. So that's all real similar to the E1. Now, the thing that's different about the E1 that you mentioned is the extremely high voltage that can happen, like around 50 kilovolts per meter. And we've tested our relays by going to third-party labs and subjecting them directly to an electromagnetic field that's 50 kilovolts per meter,
and that's a lot, by the way.
Yeah, your typical antenna from a walkie-talkie somewhere around 10 to 30 volts per meter, and here we're testing it 50 kilovolts per meter, so a lot different.
3 orders of magnitude larger,
yes.
Right? So that's amazing. Well, let's pull on that thread then. I don't think we're going to be able to actually detonate a nuclear weapon anytime soon on our own volition, right? Not that I want to by any means. Don't get me wrong. So how do we go about really simulating hemp in a realistic way so we can understand really if an event were to happen, what the impact might be on electronic equipment like ours that's critical for critical infrastructure?
Yeah. So our U.S. government released what I'll call just the baseline waveform, that 50 kilovolt per meter pulse, described by, roughly a nanosecond rise time with a 23 nanosecond fall time for all the engineers among us. And when we break that up into its constituent parts, we have test generators in the lab that can perform a series of tests on each part of that waveform that we discussed, the E2 and the E1. So we break it up into pieces and we do a series of about 6 tests that when you put them all together, add up to that HEMP event.
So that's really cool. So based on your experience, your researching, all the testing you've done, what would the likely effect of an EMP or HEMP event be on the power grid?
The most likely event is nothing, right? So
why is that? Now, does it have a lot to do with where how high the weapon is, how the power lines, if they're going north south or east west, and how that coupling happens?
Yeah, and I'll clarify. Almost all the equipment on the grid will continue operating. So, and that's because it takes so many special things to come together to get the full effect of 50 kilovolt per meter. Yeah, the waveform has to be aligned just perfectly with the conductors on the ground. It's detonation height, angle of incidence, the polarization of the wave, all of those things have to line up to get the maximum event. You'll probably remember when we were kids that when our fathers wanted to watch the football game, they'd always make us hold that antenna and move that around. And it was impossible to get that signal to stay perfect. And that's about all the things that would have to line up to get this perfect, HEMP event to where the worst case scenario happens and you were to damage a device. So I think a worst case situation you'll look at is maybe 1% of the transmission substations might be affected to the point where they'd have a relay that needs to be repaired.
And if we take it at that 1%, are we talking electronic devices that are most likely to be impacted or other primary equipment?
That's electronic devices.
Yeah. How you're a manufacturer of electronic devices, right? So if I had a substation in, I don't know, someplace in the country that did have that 1% where a relay or some other PLC or something was affected by it, it seems to me that you could roll a truck pretty quick, right? Now, of course, a nuclear weapon just went off over your head, right? So you got some other things you might want to have to consider about what's going on. But right, the physical act of getting an electronic device to get the grid up probably seems like within a day or something. Like we're able to replace entire substations after a hurricane rolls through. In a matter of weeks, we can have the power back on. So it seems to me this is a 1%, pretty limited, and the ability to do some supply chain support for an affected area of the country seems pretty reasonable.
Yeah, and I think that's key, that what we're talking about here is prevention of a protracted wide area blackout, which is just not going to happen. You'll lose a few relays and you'll do just that. You'll have them in spare inventory, or we'll be able to make them within a few days and you'll be up and running again.
At some point, hemp and EMP can become a pretty divisive discussion, right? It doesn't seem to ever go away. I think people have been debating this now for, certainly you and I have been involved with this for, 10 years or so. I recently read about a new research article by the U.S. Geological Service and the University of Colorado, where they were measuring the impacts of EMP based on various depths or composition of the earth between the event. For example, and the difference in conductivity between an igneous and sedimentary rock can affect how much current can be generated for some of these events. Based on research they conducted, that EMP hazards have not been accurately map tested in complex geological settings. Does this research change your thoughts on EMP or hemp as a potential threat to the grid? And does it change how you would go about testing products going forward?
It doesn't, because certainly we've started with the worst case scenario. That's what all the first research was for, right? Or was centered around. Come up with the first or the worst case scenario for these situations. And that's what we did. And if there are arguments being made that it can be even, worse than what we thought was worst case for this type of an event, that's talking about the late time or the E3. Yeah. And that takes minutes to manifest itself, by which time we've got protective relays out there measuring the harmonic content into the transformer, the temperature of the transformer, and we can start taking mitigating actions. We have time to react to the E3 event, which that research is is centered around.
So this is that's interesting, right? Because then there's this E3 is similar to the geomagnetic disturbances that get created by coronal mass ejection, right? This quasi DC that there's some concern about generators and some transformers and some generators and how the heating may happen in these particular devices due to this quasi DC current that can cause some semi-saturation, some other things that cause heating. I guess my thoughts on that is we've certainly studied the GMD, the geomagnetic, and which you've been another. This is all these magnetic events just seems to be in your wheelhouse right now. And not to go too far off topic on HEMP, do we think that GMD is going to cause the same problems that EMP could?
If it were to cause problems, yes. But we've got space-based stations right now that are monitoring for coronal mass ejections. And each time we get notified that there was a major storm event, I call our field application engineers and say, hey, there was this big event. Have our customers reported anything? And to this point, it's been, nope, no reports, all quiet here.
Yeah.
Right. So I think the transformers are pretty robust, as some of the research has said. When we talk about the 1989 event, there were a lot of
the Carrington event.
The Carrington event was in the early 1900s, right? When the telegraphs were affected. Yeah. So if you're using the Carrington event to talk about a baseline event that's very strong, then yes, it's synonymous to that. So there was a lot of mitigating factors to that went beyond just the geomagnetic storm. They had a transformer out for, maintenance, and the technology was old enough that it couldn't detect the signal. We've got all that going for us right now. And research at the last National Energy Regulatory Corporation meeting that I attended on the topic, they had scientists there presenting, saying that transformers in Canada are subjected to this all the time. We just don't have anything up there to measure them. So that was their conclusion, that they're riding through it right now.
Yeah. Excellent. All right. Back to EMP. What are some of the EMP mitigations that SEL builds into our devices?
So my favorite one is just space between the circuits, right? not allowing there to be a small enough air gap to get that electrostatic discharge.
Yeah.
Right. So space is one of them. And then for some of our circuits, just the size of the components we use, they're designed to eat energy, for lack of a better term. So they're designed to operate in a high electromagnetic environment, like lightning strikes and the indirect effects of lightning strikes, and they're just designed for it. So that's a little bit different than your typical wall charger that you're going to find.
You've always been a great collaborator. What else is going on in our industry? Are you working with other folks on discussing EMP mitigation strategies, or what should we be doing as an industry together to make sure that if there is a problem, how we go about solving it collaboratively?
Yeah. So right now there's two activities that I'm really excited about. There's an IEEE task force on EMP mitigation that we're working on, and that's really great. Because
what are we doing there specifically?
We are working with our friends at EPRI and others as well, and Dr. Bill Radasky, who's a renowned EMP expert. He's part of that committee too. And what we're working on there is refining the models that we use to simulate the effects of an HEMP. As I mentioned before, we've started out with some very simplistic models. And as you mentioned, it's not like we can light one of these things off to see, right? So what we're learning is as you add more and more elements to the model, the effect gets less and less and less. So we want to agree as an industry on how we're going to model this to get a realistic simulation result. Because of course I can appreciate doing the worst case model, because if you can live through the worst case, then everybody walks away happy. What we found with the worst case model is that not all devices are resilient to that worst case model.
Right.
So right now, refining that model is key, and I'm happy with how the industry's collaborating to do that through the IEEE and NERC.
Well, that's cool. Along with the work you're doing with EPRI, and certainly our utility friends are part of EPRI, and I'm sure they have a vested interest in helping with the modeling and understand the outcome. What other ways are utilities preparing for an EMP event if that's on their roadmap of things to be concerned about?
Yeah, so they're certainly eagerly awaiting, for the results of the IEEE and NERC work. But right now, our position is that if your substation has demonstrated lightning immunity, then it has a good deal of immunity to HEMP. I understand that our utilities are sometimes very conservative. They want to be very safe. And if they take that position, then some simple things they can do are things like install shielded cable in the substation yard and ground that cable at both ends. I know the historic practice has been to ground it at one end only, but for HEMP, we recognize that it's better to ground it at both ends. They could also place metal oxide varistors at the output of their potential transformers. Now, metal oxide varistor is just a bigger version of the surge suppressors that we have in our homes. And that just makes you more resilient to lightning, right? Which is more likely to cause damage than an HEMP. So when you do those things, you just get a better substation all the way around.
I bet you're right. I bet during the year there are more lightning strikes than EMP events. I'm just guessing.
Just guessing.
Yeah, I'm just guessing. But and I think you brought up a good point, right? If I was a utility, I'd really like to get behind the EPRI study to understand what, if anything, do I really need to do? Because there's a lot of problems a utility has to solve every single day, right? And is this EMP thing, a 1 out of 10, or is it a 10 out of 10, or maybe an 11 out of 10 or something like that? And I think the work you guys are doing there and the ability to provide really good data so a utility can make an informed decision on how to allocate, precious resources is the right thing to do.
Yeah, and that's key. And I think what our utilities are going to realize once they see the probability of this, once the models are done, is that the probability is so small that they're only going to want to take mitigating action on the most critical transmission substations.
Yeah.
And it'll be simple, just like we talked about.
Simple is always good. It's it's relatively easy in terms of availability and even cost for utilities to maintain inventory of backup equipment to use in the event of a damage to a portion of their power systems. Like when lightning hits and maybe, blows up a recloser control, though that doesn't happen very often. Or maybe even more so, the unlikely event of an EMP strike. But what if an MP or HMP event took out a transformer? Those are some big assets, and they're probably too expensive just to have them sitting around in a yard waiting to be installed somewhere. What are your thoughts on that?
My thoughts are that is such a low probability of occurrence for the reasons we mentioned. Everything has to line up just perfectly to get enough energy from an EMP to damage a transformer that it's, likely to be damaged in other ways. And they've already got risk assessment plans for that. So I wouldn't be one to promote having transformers on spare in case of an HEMP.
So that's interesting, right? There's risk associated with everything, right? And probably for a transformer as an example, it's like, well, there could be some bad oil, or there could be like an insulator failure, or there could be, right? And the probability of those maybe aren't much bigger, much lower than an EMP event. Maybe the EMP event is even lower than that, right? So there's risk associated with everything we do, everything we operate and manage, right? So it comes down to a risk tolerance to whatever that event is. That's really, really interesting. I think you're right. I think the likelihood of a transformer or some major piece of apparatus being damaged is probably pretty low. There's other things that would be more likely, like a hurricane if you're in the southeast, or earthquake if you're on the west coast, or something like that.
Precisely.
Yep. And to your point, utilities have to take all of those sorts of contingencies in plan when they're talking about stocking or having replacement in place. There's been a lot of research done on EMP topic, and there are standards and regulations in place to mitigate damage to the power system from this type of event. Is there anything else you'd like to see happening in regard to protecting the electric power system?
I think just underscoring the collaboration that we're doing in the IEEE committees and with NERC, just getting those models refined and out in the open for peer review, scientific method, and then as an industry agreeing on that, yes, this is the model that we want to use to create standardized testing around them.
So I know there's been some activities, we've been talking about EMP for 10 years. Are we getting better at collaborating and agreeing on the models and the math, or kind of about the same level, or is it getting worse?
I think having the forums like the IEEE and NERC are advancing that quite a bit.
Yeah.
Because we get our utility customers involved, the research labs involved, the manufacturers involved, industry experts involved, right? All at the same place. So it is collaborative by nature to get a body of work through the IEEE committee. So yes, I think it's fantastic what's going on right now.
That's great. I really like the idea of everybody sharing their data or their assumptions or their models, right? And then let's have a rigorous debate on what it is. And then based on those results, let's go out and figure out if we need to do anything to harden the power system or not. Well, Travis, thank you. I think
pleasure.
my mom's going to enjoy listening to HEMP discussions, and I think she'll get a lot out of it, along with, I hope, all our technical listeners too.
My pleasure.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.